People have been interested in learning how the universe came into being throughout the history of science. The theory known by most as the Big Bang Theory, which postulates that the universe began from an incredibly dense and hot point, has been the most frequently accepted explanation. Many specialists have provided evidence in favor of this theory over time. But when science develops and new technologies appear, old beliefs are called into question by novel concepts and viewpoints. James Webb Space Telescope, JWST, which has taken pictures of approximately 750 galaxies that were previously unidentified, is one example of such a breakthrough. These discoveries are challenging the Big Bang Theory's veracity and redefining our conception of the universe's beginnings. The telescope was built to aid in the study of the formation and evolution of galaxies. However, its findings have shown that these objects differ greatly from the predictions of the Big Bang Theory in terms of size, smoothness, age, and variety. These recently discovered galaxies contravene the idea that states that as the universe expands, galaxies should seem larger the farther away they are. According to the Big Bang Theory, all of the matter and energy that would eventually form stars, galaxies, and other cosmic structures came together in a singularity, a tiny, superdense point that was extremely hot. This theory, which has its roots in Albert Einstein's general relativity theory, explains how high heat and density were created in the early universe when all matter was squeezed into an incredibly compact space. For a long time, scientists thought that this hypothesis explained how the cosmos came into being. But fresh JWST evidence is now compelling scientists to re-evaluate several parts of this notion. The JWST images refute the conventional wisdom in a number of ways. Among other things, it has found galaxies that are older and more varied than anticipated. Additionally, they seem far smoother than the theory suggests. The Big Bang Theory predicts that galaxies will exhibit observable anomalies as a result of their origin and evolution throughout time. Yet, these data point to a different cosmic past. Furthermore, the distribution of galaxies found by JWST defies Big Bang expectations, which assumed a lower abundance of galaxies in the distant past. In accordance with the hypothesis, galaxies would expand through mergers and collisions, creating a chaotic, destructive universe. Nonetheless, galaxies appear more organized in the JWST photos, with less evidence of disruption or violent collisions. These findings imply that there is a gap in our knowledge of the formation and evolution of galaxies. A plethora of data continues to support the Big Bang Theory in spite of these obstacles. The distribution of atoms like hydrogen and helium, the observed redshift of light from far-off galaxies, and the cosmic microwave background, CMB, radiation, for example, all lend substantial support to the idea. The cosmic microwave background, CMB, is a feeble radiation that was detected in 1965 and is thought to be the remnants of the Big Bang. Its regularity and dispersion of temperatures strongly imply that the cosmos was once extremely hot and dense, and that it expanded and cooled over billions of years. But the JWST's results are making scientists re-evaluate some parts of the idea. For instance, the theory that galaxies should only have begun to form after a specific amount of time after the Big Bang is called into question by the discovery of galaxies that seem to have formed considerably earlier than previously believed. Images obtained with the telescope reveal galaxies that appear to be significantly larger and more developed than anticipated, particularly at redshifts higher than 10, which raises the possibility that these galaxies formed considerably earlier than the theory predicted. Due to these differences, several scientists have put up different theories on the beginning of the universe. One such theory is the cyclic universe model, which postulates that the cosmos expands and contracts indefinitely. Though these novel theories come with their own set of difficulties, they provide fascinating avenues to account for the surprising JWST results. Furthermore, the JWST's high-resolution photos offer hitherto unheard-of insight on how stars and planetary systems evolve. Scientists can learn more about the mechanisms governing star formation and the evolution of potentially habitable habitats by observing the light emitted by far-off stars and the gas and dust in their immediate surroundings. Understanding how the conditions required for life might develop elsewhere in the cosmos depends on this knowledge. To sum up, the James Webb Space Telescope has produced an abundance of fresh information that is changing our perception of the early universe. These new findings cast doubt on several of the fundamental tenets of the Big Bang Theory even if it is still a robust and well-supported theory. Scientists may have to rewrite our cosmic history and take into account new hypotheses as they continue to examine the JWST data in order to account for the unexpected complexity of the early cosmos. This ongoing research serves as an excellent example of how scientific inquiry is dynamic and always expanding due to the introduction of fresh data. Not only do the findings of the James Webb Space Telescope, JWST, cast doubt on the Big Bang Theory, but they also provide new insights into the nature of cosmology as a whole, the origin of galaxies, and the evolution of the universe. The JWST data offers a once-in-a-lifetime chance to re-evaluate the fundamentals of cosmology, astrophysics, and our position in the universe. This in-depth investigation digs further into the ramifications of these findings, how they contradict pre-existing theories, and how scientists are adapting to these novel situations. Launched on December 25, 2021, the James Webb Space Telescope is a new window into the cosmos and the replacement for the Hubble Space Telescope. It is currently the most powerful space telescope ever constructed. JWST is designed to be used for infrared observations, in contrast to Hubble, which is primarily used to catch visible and ultraviolet radiation. This is a significant distinction because infrared radiation can penetrate dust clouds that block off most visible light in space, enabling JWST to see parts of the universe that were previously out of our line of sight. The sensitivity and resolution of JWST are significantly higher than those of any previous technology. Its cutting-edge tools and optics are made to provide for an unmatched level of detail in the study of star and planetary system formation as well as galaxy development. This opens up the possibility of studying not only the early history of the universe, but also its current state, which may provide new light on the formation of planets, stars, and galaxies. In light of this, the telescope may essentially peer back in time by observing galaxies at such large distances that it has taken billions of years for their light to reach Earth. Studying the epoch of reionization, which took place in the early cosmos about 400 million years after the Big Bang, is one of JWST's main objectives. The first stars and galaxies emerged during this period, and the ionization of the surrounding hydrogen gas by the light from these stars caused the cosmos to change from opaque to transparent. JWST's observation of this epoch can yield valuable insights into the circumstances surrounding the formation of the first galaxies and, more significantly, into the processes by which the early cosmos changed into the ordered and complex universe we see today. For many years, the Big Bang Theory has been the primary theory used to explain the universe's beginnings and development. This theory states that 13.7 billion years ago, the universe began as an impossibly dense point known as a singularity and then rapidly expanded, a process known as the Big Bang. This occurrence prepared the way for matter to cool and form, eventually combining to form stars, galaxies, and the intricate structures we see in the universe today. The discovery of the cosmic microwave background, CMB, radiation, the distribution of galaxies throughout the universe, the redshift of light from distant galaxies, and the relative abundance of light elements like hydrogen and helium all contributed to the long-held belief that the Big Bang Theory had a strong foundation. But according to JWST data, the early cosmos might have been more complicated and formed in a different way than previously believed. Some of the galaxies discovered by the JWST, for example, appear to have formed far earlier than predicted, some as early as a few 100 million years after the Big Bang. This defies earlier theories that proposed galaxies formed more slowly. Moreover, a significant number of recently discovered galaxies seem to be more advanced than anticipated given their age. They possess more complex characteristics, larger structures, and mature star populations than what the Big Bang Theory would anticipate for galaxies at such an early stage of development. Cosmologists are being forced to re-evaluate the galaxy creation and evolution timeframe in light of these results. What does it mean for the rate at which the cosmos cooled and developed following the Big Bang if galaxies formed so early and completely developed? Was the expansion rate more rapid than previously thought? Is it possible that we have not yet considered other mechanisms, such as interactions between dark matter, dark energy, and ordinary stuff? Cosmic inflation is one of the main tenets of the Big Bang Theory. According to this theory, the universe expanded significantly more quickly than the speed of light in the initial few minutes following the Big Bang. It is believed that the inflationary phase corrected any anomalies, and prepared the groundwork for the subsequent, more steady expansion. The reason behind the universe's large-scale homogeneity and isotropy now is inflation. It also explains why, despite their great distances from one another, remote areas of the universe exhibit comparable physical characteristics. The inflationary hypothesis itself is still lacking, though. It does not address the exact development of galaxies or explain how the initial density fluctuations that would eventually become galaxies and clusters of galaxies formed, even though it successfully accounts for the universe's uniformity. Knowing the structure of the universe depends on these fluctuations. Observations with JWST have revealed traits in some of the oldest galaxies that are inconsistent with cosmic inflation theories. For instance, compared to inflationary models, many of the found galaxies seem to have formed far sooner and more fully developed. Some scientists wonder if inflation alone tells the whole story because of this disparity between the theory of inflation and the actual observations from JWST. Is it possible that an additional mechanism sped up or initiated the development of galaxies in the early universe? The interplay between dark matter and conventional matter throughout the early stages of the cosmos could be one explanation. It is believed that dark matter, to account for around 27% of the mass energy content of the universe, but it interacts mostly through gravity rather than electromagnetic forces. Its presence would have acted as a gravitational scaffold around which galaxies may develop, so influencing the dispersion of galaxies. Understanding dark matter's precise function in the early development of galaxies is still a difficult task, though. Even though JWST has significantly advanced our understanding of how galaxies originate, it has also brought to light the gaps in our knowledge of dark matter and dark energy. Because dark matter does not interact or emit electromagnetic radiation, its gravitational effects on galaxies and galaxy clusters have allowed for indirect observations of the material. On the other hand, the universe's accelerated expansion is assumed to be caused by dark energy. The idea that interactions between dark matter and dark energy may have generated the huge, complex galaxies observed by JWST is a fascinating one. The gravitational effects of dark matter are well understood, but little is known about how it interacts with normal matter and dark energy. The JWST data may indicate new interactions between dark matter, dark energy, and ordinary matter since it shows galaxies that appear to have formed earlier and more thoroughly than predicted. In ways that we haven't fully predicted yet, dark energy may have expedited the birth of galaxies. The timescale for galaxy formation in the early universe has been called into doubt due to the JWST's unprecedented ability to peer further back in time. The Big Bang Theory states that galaxies shouldn't have formed until the universe had cooled down enough for matter to congregate and form stars, which should have happened several hundred million years after the Big Bang. Nevertheless, galaxies that JWST has shown to be more developed than previously believed are developing as early as a few hundred million years after the Big Bang. The fact that some of these galaxies appear to have built gigantic structures when the universe was 500 million years old, complete with star clusters, intricate spiral characteristics, and even evidence of galactic mergers, is a momentous discovery. This contradicts the conventional theory of galaxy formation, which holds that smaller groups of gas and dust eventually gave rise to galaxies. These results suggest that either a far quicker than expected rate of galaxy formation occurred, or that an additional mechanism contributing to an accelerated process of galaxy growth, possibly including dark matter or dark energy, was involved. These results may have consequences for the nature of cosmic reionization, the time when the cosmos became transparent after going from being opaque, because they may have contributed to the ionization of surrounding hydrogen gas earlier in the universe's history. The early galaxies discovered by JWST may have been more important in this process than previously thought. This could change the ideas of how the universe evolved from the cosmic dark ages to the more ordered and light world we observe today by indicating that the reionization epoch happened far earlier than previously thought. In light of the JWST's unexpected results, some cosmologists are starting to re-evaluate hypotheses other than the Big Bang Theory. The cyclic universe theory is one such model that postulates an endless cycle of expansions and contractions throughout the universe. This theory holds that the universe continuously cycles through phases of expansion and collapse rather than having a single beginning or finish. Because it may resolve some of the inconsistencies in the Big Bang model, especially those brought about by the finding of galaxies that appear to have formed earlier than anticipated. The cyclic universe idea has drawn interest. It's plausible that some of these early galaxies weren't born from the Big Bang itself, but rather were the remains of a former cosmic age if the universe has seen cycles of expansion and contraction. Although this theory is still theoretical and has its share of difficulties, it presents a compelling alternative to the Big Bang theory. The cyclic model might offer a fresh viewpoint on the possible emergence of galaxies, stars, and other structures in the early cosmos. It might also aid in explaining the surprising results obtained by the JWST.